Hello, and welcome to this video about overdetermined linear systems of equations. This video is a part of the ECMI modeling course mobile phone positioning topic. In this video, we will discuss overdetermined linear systems of equations and the least squares method. We will discuss the path loss model, we will have a peek at the data we are working with, and we will use the path loss model to estimate model parameters in the linear case when the access point location is known. So, let's go on to some linear systems. Consider the following linear system of equations. We have matrix A, the vector of unknown variables x, and the vector y. Let us assume that matrix A is linearly independent. Now, if m is greater than n, that is to say you have more equations than you have variables in x, the system is called overdetermined. In this kind of a case, generally there is no exact solution for the system. One useful approach to solving this kind of a system is the least squares solution, which minimizes the difference between y and a times x. The way in which the least squares solution is found is not the topic of this video, but you can try to prove this statement here. The solution itself looks like this, and if you are using MATLAB to solve these kinds of problems, we recommend you use the backslash operator to save time. This way you don't need to calculate everything separately. This was a short recap of linear systems for now. We will use this knowledge later. Let's move on to the path loss model. In order to better understand the path loss model, it's useful to get familiar with the basics of indoor positioning. When we consider indoor positioning, it's easy to understand that satellite signals won't help us much, since satellite signals won't reach you indoors. One method of indoor positioning uses Wi-Fi network signals to position users inside buildings. For our purposes in this video, an access point, also referred to as an AP, is a Wi-Fi transmitter located inside a building. The AP sends out a signal at some strength, and the receiver, usually a mobile phone, picks up a signal that has been affected by the distance from the transmitter and the physical properties of the building. The path loss model aims to describe both of these. The path loss model is a method for estimating the path loss parameters and location for a single access point. In this first case, the location of the access point is known. Later we will take a look at a case where the access point location is unknown. The path loss model is defined as written here. Here the P is the received signal strength value, A_S is the apparent transmission power, N is the path loss exponent, and D is a distance between the transmitter and the receiver. The W stands for noise, but we will dismiss the W for now. Next, we will take a peek at the data. This exercise contains a data file called wlandata.mat, which contains the following data. There are in total a little over 1400 rows. The first column is the column of timestamps. The second and third columns are for x and y coordinates, and the rest of the columns are for each access point containing their received signal strength values. If the access point was accessed from the coordinates on row n, then the nth value of the access point column has a non-nan value. Otherwise the value is nan. Here you can see a visualization of the data. Every time you see something blue, that means that the value is a real number instead of a nan value. If you consider the path loss model together with our data, you can see that the problem for calculating the parameters is quite different if the AP location is known or unknown. If you know the location of the access point, you can calculate D. If D is known, you can calculate the logarithm. And if you can calculate the logarithm, This allows us to solve the problem as a linear least squares problem, written here. We will now do this in MATLAB. Okay, so we have previously written this exercise, and we will now walk you through it. The objective is to calculate the pathless model with a known access point location. And we will start by loading the VLAN data and AP location math files into MATLAB. You will notice that the AP location contains the x and y coordinates and the index of the known access point. Next, we want to pick the x and y coordinates of measurements and the received signal strengths of this access point from the learned data matrix. We will do this now. Notice that we have the +3 here, so that we will get the index right. Next, we will cut out the not a number values. There are different ways to do this, but we have done it like this. Now AP contains all the received signal strength values and coordinates of measurement points for a single access point located at AP location. All necessary for calculating D is known, so we calculate D. And now we can create the pathless model in the style of y is a times x. Note that y is here the received signal strength column of AP. As mentioned in the slides, matrix A, is a matrix of ones and -10 times the logarithm of D. And finally, we can solve the x with the backslash operator. Let's look at the values provided by x. So here we have the value for AS, and here we have the value for N. Now we might ask ourselves, does our result describe the physical properties of our system? We can first plot the received signal strength values as a function of distance. Let's do that now. You can see that this forms a quite nice data set. Let's fit a line into this data. Notice that the fitting has to be done using logarithms, since the x-axis is logarithmic. Now you can see that there's something weird going on here, right about here. This would mean that we have received signal strength values of -10. These seem to be outliers. So let's take a look at the data more closely. As we have sorted the variable AP, we can go all the way down, and we see that this -10 is definitely an outlier. So let's get rid of that and see what happens. This gets rid of the outliers. Let's run the code again. Now we get a much better fit, and the data looks cleaner. Finally, let's make the data more readable. And there we go. The pathless model allows us to present a large number of positioning data with just a few variables. Next, we will take a look at the nonlinear case where the access point location is unknown and calculate the pathless model there.